Welcome to Night Shift Knowledge, a quiet place in the late hours where you can finally let go of the day. Take a moment to settle in, soften your shoulders, and allow the busy world to fade completely into the background. Tonight, we are going on a gentle journey through the fascinating corners of science, biology, and history. Before we begin, please know that the screen will fade to dark very soon. You can safely rest your eyes and leave this video playing as you drift off to sleep. I would also love to hear from you. Please leave a comment below with a general topic you would like me to cover in a future video. It is always a pleasure to read your ideas and shape this channel around what brings you peace. If you find comfort in this space, a like and a subscribe would be deeply appreciated. To ensure the next video quietly finds its way to you, please tap the notification bell. So as your breathing slows and your room grows a little darker, let your curiosity drift along with my voice. Let us begin. Colder than the void. 6,000 light years from Earth, a dying star is exhaling. Gas and dust are expanding outward at such speed that they chill the surrounding void to a degree that seems impossible. Here, in the deep freeze of the cosmos, the temperature drops to 1 degree above absolute zero. It is the natural limit of the universe. The dead of winter on a galactic scale. But the coldest place in existence is not out there. It is here, in the center of a bustling city, surrounded by the hum of traffic and the warmth of a living planet. Inside this room, a small team of physicists is engaged in a battle against nature itself. They are not trying to generate heat, they are trying to steal it. They are chasing a temperature so low it defies the physics of the universe that created us. They have reached a temperature of 50 picokelvins. That is 0.0000000005 degrees Kelvin. To put that in perspective, the empty space between the stars, the background radiation of the entire universe, is 50 million times hotter than this spot in Cambridge. On Earth, we have beaten the void. We have created a cold that does not exist in nature. But to understand how we got here, we first have to understand why space itself isn't cold enough. In the beginning, the universe was fire. As space expanded over billions of years, that primordial fire stretched out. It cooled, but it never truly disappeared. It merely faded into a faint, invisible glow. This is the cosmic microwave background radiation. It is the afterglow of the Big Bang, the first light that was ever free to travel through the cosmos. It saturates every inch of the universe. It hits the Earth, the Moon, and the most distant galaxies constantly. Because of this omnipresent bath of ancient energy, empty space can never naturally get colder than 2.7 Kelvin. That is minus 270 degrees Celsius. It is unimaginably cold to human senses, cold enough to freeze air solid. But to a physicist, 2.7 Kelvin is actually quite warm. It is noisy. It is chaotic. That background radiation is like a constant static hiss that never stops. To break the natural limit, to go colder than the void, you have to hide. You have to build a shield that can block the echo of creation itself. This is the challenge Wolfgang Ketterle accepted. A Nobel laureate and a pioneer in the field of ultra-cold physics, Ketterle doesn't just study cold, he hunts it. In his lab at MIT, the equipment required to reach these temperatures is massive. It takes up an entire room, a sprawling labyrinth of lasers, magnets, and vacuum pumps. It is a Rube Goldberg machine designed to do one simple thing: stop motion. Temperature is not a substance. It is a measurement of motion. When an atom moves fast, it is hot. When it stops moving, it is cold. Absolute zero is the point where all atomic motion ceases. Kettle's team uses lasers not to burn but to cool. They use a technique called laser cooling, firing thousands of photons at a cloud of atoms from every direction. Imagine trying to walk through a crowded room. If people bump into you from all sides, you are constantly pushed back. You can't move forward. The photons act like a microscopic molasses, slowing the atoms down until they are barely moving at all. But lasers can only get you so far. To reach the picokelvin scale, temperatures a billion times colder than deep space, you have to leave the material world behind. The team turns off the lasers. They turn on powerful magnetic fields. They strip the atoms of their ability to interact with the walls of the container, effectively isolating them in a perfect vacuum. Then, they allow the hottest atoms to evaporate away, leaving only the coldest behind. It is a process of subtraction, removing energy, removing motion, removing noise, until, in a chamber no bigger than a coffee mug, they create a state of matter that shouldn't exist. 50 picokelvins. In this microscopic corner of Earth, the atoms are so still they seem to be paused in time. They are colder than the space between the galaxies. We have conquered the cold, but in doing so, we have opened a door to a strange new world. At these temperatures, matter stops behaving like matter. It becomes a wave. It flows without friction. It defies gravity. But cold is not just an absence of heat. It is a canvas for the impossible, and we have only just begun to paint. The quantum refrigerator. In our previous journey, we witnessed the cosmic deep freeze, a dying star exhaling gas until the surrounding void dropped to just 1 degree above absolute zero. It is a temperature so low it challenges the very laws of nature as we know them. But out there, in the vast emptiness of space, the cold is a passive byproduct of expansion. It is an accident of physics. Here on Earth, we are not content to merely watch the universe freeze. We want to command the cold. We want to create it on demand, in the heart of a room temperature laboratory. And to do that, we have to turn to one of the most counterintuitive ideas in scientific history. We have to use heat to create cold. We have to take some of the most intense, high-powered energy sources we have, lasers, and aim them directly at matter with the specific intention of freezing it solid. It sounds like madness. It sounds, as one physicist famously quipped, like using a fire hose to put out a candle. But in the strange, submicroscopic world of quantum mechanics, this isn't just possible. It is the only way to reach the coldest temperatures in the universe. To understand how light, a carrier of energy, can steal energy away, we first have to change how we look at the atom. Imagine an atom not as a solid ball, but as a tiny, frantic engine. Heat is simply motion. The faster that atom vibrates, the hotter it is. To cool it down, to freeze it, we need to slow it down. We need to apply the brakes. But you can't just reach out with a pair of tweezers and stop an atom. You need something that can travel at the speed of light. You need photons. This brings us to a phenomenon you experience every day, usually without noticing: the Doppler effect. You hear it when an ambulance speeds past you. As the ambulance approaches, the siren's sound waves are compressed, pitching the sound higher. As it drives away, the waves are stretched, dropping the pitch low. Light behaves in exactly the same way. To an atom moving towards a beam of light, the light waves appear squashed. Their frequency seems higher. To an atom moving away, the light seems stretched out, lower in frequency. This quirk of nature is the key to the quantum refrigerator. Atoms are picky eaters. They don't just absorb any light that hits them, they only absorb photons that match a very specific energy frequency, like a tuning fork that only vibrates at one specific note. If the light is slightly off-tune, the atom ignores it completely. Here is the trick. Scientists tune their lasers to a frequency just below the atom's natural absorption frequency. If the atom is sitting still, the light passes right by it. It's too low energy to be absorbed. But if the atom is moving towards the laser beam, the Doppler effect shifts the light up. Suddenly, the frequency is perfect. The atom opens its mouth, so to speak, and swallows the photon. But this isn't a free lunch. That photon carries momentum. When the atom absorbs it, the impact acts like a tiny head-on collision. The atom slows down, it loses a fraction of its speed, it gets colder. A fraction of a second later, the atom re-emits the photon, shooting it out in a random direction. But because that emission is random, the kicks cancel out over time. The only effect that remains is the slowing down from the head-on collision. One laser can only slow atoms moving in one direction. But atoms in a gas are flying in every chaotic direction imaginable. To catch them all, we need to surround them. We need what is known as optical molasses. In 1985, a physicist named Stephen Chu and his team at Bell Labs set up an experiment to do exactly this. They arranged 6 lasers pointing up, down, left, right, front, and back, all tuned to that specific below resonance frequency. They turned them on inside a small vacuum chamber containing a cloud of sodium atoms. The result was mesmerizing. No matter which direction an atom tried to run, it was always running into a beam of light that was tuned to stop it. It was like trying to swim through thick syrup. The more the atom struggled, the more the photons pushed back. They were trapped in a viscous, glowing grid of pure light. Chu had effectively created a refrigerator made of nothing but light. He had chilled the sodium gas to 240 millionths of a degree above absolute zero. That is colder than the Boomerang Nebula. It was a breakthrough that would eventually earn him the Nobel Prize. For a moment, it seemed we had reached the bottom. But there was a problem. The optical molasses was incredible, but it had a flaw. The Doppler cooling technique hits a limit where the heating caused by the random emission of those photons balances out the cooling from the laser impacts. The atoms keep jittering. They never quite stop. To reach the record-breaking temperatures we aim for today, to see the quantum world in its true, undisturbed form, lasers alone are not enough. We have slowed the atoms down, but we haven't stopped them. To go deeper, to cross the threshold into the truly unknown, we have to stop being gentle. We need to stop fighting the motion and start removing the movers entirely. We need a method that doesn't just cool the gas, but fundamentally changes its state. We need to get aggressive. Double the race to the superatom. The transition from the cosmic void to the sterile lab is jarring. In the previous chapter, we stood in the shadow of the Boomerang Nebula, witnessing nature's ability to chill the universe to just 1 degree above absolute zero. Here, under the hum of fluorescent lights and the glow of computer monitors, humanity is trying to beat that cosmic benchmark. But to understand how we got to this point, how we learned to freeze matter itself, we have to step away from the stainless steel and travel back in time. The year is 1924. In a quiet study in Dhaka, British India, a physicist named Satyendra Nath Bose puts the finishing touches on a letter. It's a paper he has written in English, but his attempts to publish it have failed. The editors simply don't understand what he's proposing. In a final act of hope, he mails the manuscript to the one man on Earth who might, Albert Einstein. Einstein realizes immediately that Bose has stumbled upon something profound. He translates the paper into German himself and gets it published. But Einstein doesn't stop there. He takes Bose's statistics on photons, particles of light, and applies them to atoms. In doing so, he makes a terrifying and beautiful prediction. Einstein theorized that if you cool a gas of atoms down to temperatures near absolute zero, something impossible should happen. The atoms, usually distinct individuals bouncing around like billiard balls, would suddenly lose their identities. They would collapse into the lowest possible energy state, effectively becoming a single, giant superatom. It was a fifth state of matter, predicted on paper, but seemingly unreachable in reality. For 70 years, this Bose-Einstein condensate remained a ghost in the machine. It was the holy grail of low-temperature physics. Theoretical physicists argued about what it would look like, while experimental physicists struggled to find a way to get cold enough. You see, the Boomerang Nebula is cold, but to create a condensate, you need temperatures 1,000 times colder than that. You need to reach the nanokelvin scale, a billionth of a degree above zero. By the mid-1990s, the technology finally caught up with the theory. Lasers had become precise enough to slow atoms down, and magnetic fields strong enough to trap them. But physics is rarely a solo endeavor. It was no longer just a quest for knowledge, it had become a race. Two of the world's leading labs were locked in a high-stakes battle to be the first to witness the impossible. On one side, you had the team at Gila in Colorado, Eric Cornell and Carl Wieman. They were brilliant, methodical, and desperate to finish first. On the other side, at MIT, was Wolfgang Ketterle. He had fewer resources but a fierce determination. The scientific community watched with bated breath. The pressure was immense. To win, they had to trap a cloud of rubidium or sodium atoms and hold them perfectly still. The hurdle wasn't just cooling, it was holding on. Atoms at these temperatures are incredibly fragile. If a single stray molecule of room temperature air hit the cloud, it would be like a bowling ball hitting a house of cards. They needed a vacuum chamber emptier than the space between galaxies, and a magnetic trap so precise it could hold the atoms without heating them up. To get from very cold to quantum cold, they employ the technique that is surprisingly familiar. Imagine a hot cup of coffee. You want to cool it down, so you blow on the steam. What are you actually doing? You're knocking the hottest, fastest-moving molecules, the ones carrying the most energy, off the top. The ones left behind are the slower, cooler ones. The average temperature drops. This is evaporative cooling. In the lab, they lower the lip of the magnetic trap just enough to let the most energetic atoms escape. As the high-energy atoms fly away into the vacuum, they take their heat with them. The remaining atoms rethermalize at a lower and lower temperature. They do this again and again, stripping away the heat layer by layer until only the coldest, slowest atoms remain. It was June 5, 1995. In the Gila laboratory in Colorado, the tension broke. Eric Cornell and Carl Wieman stared at a computer screen. They had been running their evaporative cooling cycle, watching the temperature plummet. Suddenly, the data changed. A sharp peak appeared in the velocity distribution. It wasn't a smooth curve anymore, it was a spike. It was the signature of a Bose-Einstein condensate. They had done it. For the first time in the universe, outside of a neutron star, they had created a superatom. But the race wasn't entirely over. Just 4 months later, Wolfgang Ketterle at MIT crossed the finish line with his own setup using sodium atoms. His condensate was larger, purer, and offered a clearer look at this strange new state of matter. The world had 2 winners, and the Nobel Prize would eventually be shared among them. But the discovery raised a new, even more compelling question. They had proven the theory correct. They had created the condensate. But how far could they push it? They were hovering just nanokelvins above absolute zero. Could they go colder? Could they reach that theoretical limit where motion stops entirely? The team at MIT wasn't done yet. They wanted to push the limit to see what happens when you strip away almost all the energy a particle possesses. The creation of the BEC was a milestone, but it was also just a starting line. They had unlocked the door to the quantum world, but now they were about to step through it into a realm of physics that is even stranger. A realm where matter behaves like waves and where temperature becomes a concept that begins to lose its meaning. The Gila team had made history, but the MIT team was looking deeper. They weren't just satisfied with creating the superatom, they wanted to control it. And to do that, they had to confront the fundamental laws of the universe that said, you cannot go colder than this. How do you cool something that is already barely moving? How do you fight the quantum jitters that exist even at absolute zero? The race to the bottom was far from over. In fact, it was about to get much colder. EI, matter, becomes wave. We left the sterile chill of the laboratory behind to journey into the past, but now we must return. We return to that stainless steel chamber, not as a prison for matter, but as a gateway to a new reality. What you are looking at is not a gas. It is not a fluid, and it is certainly not a solid in any way you've ever experienced. This is the fifth state of matter, a Bose-Einstein condensate. And in this moment, the hard, distinct boundaries of our physical world dissolve. Here, matter stops behaving like a collection of angry, colliding billiard balls. Instead, it dissolves into a symphony of probability. The particles don't just occupy space, they smear across it, overlapping until they lose their individual identities entirely. It is a transition so violent in its implications, yet so peaceful in its appearance that it defies intuition. We are witnessing the exact moment where matter becomes wave. To get here, to see this ghostly quantum tide rise in a lab, humanity had to push the limits of temperature further than ever before. We had to venture into a cold so profound that it makes the vacuum of space feel like a furnace. By the early 2000s, the race to the bottom had intensified. We remembered the Boomerang Nebula, that natural cosmic refrigerator hovering at just 1 Kelvin above absolute zero. But here on Earth, Wolfgang Ketterle and his team at MIT weren't satisfied with matching nature. They intended to break its record. They weren't just trying to cool things down, they were trying to stop the universe. The challenge wasn't just making things cold, it was holding them there. You see, cold is lonely. To strip the heat away, Ketterle's team used a process called evaporative cooling, similar to how a cup of coffee cools down. The hottest atoms are the ones with the most energy, moving the fastest. The team tuned their magnetic trap to be leaky, allowing only these energetic, hot atoms to escape. When the hot atoms leave, they take their heat with them. The remaining atoms re-establish equilibrium at a lower temperature. It's a ruthless selection process. You sacrifice the few to save the many, cooling the survivors until they are moving at a snail's pace. But to reach the record, they had to go further. They had to refine the trap itself. In 2003, the team pushed this technique to its absolute limit. They stripped away the thermal energy layer by layer with agonizing precision. They weren't battling the outside world anymore, they were battling the quantum jitter inherent in the atoms themselves. They managed to suppress the thermal motion until the thermometer read a number that strains comprehension: 50 picokelvins. That is 50 trillionths of a degree above absolute zero. At this temperature, the atoms in the cloud are moving at less than a millimeter per second. If you were an atom in this cloud, it would take you nearly an hour to travel the length of a single human finger. This is the coldest temperature ever recorded in the universe. But how do you verify something that defies standard measurement? You don't measure it with a thermometer, you measure it with a shadow. To verify the state, the scientists turn off the magnetic trap. Suddenly released from their prison, the cloud expands. A normal gas would explode outward chaotically. But a Bose Einstein condensate does something else. Because it is a wave, the expansion is coherent. It's a single, unified entity pushing outward. By measuring the speed and shape of this expansion, the scientists could reverse engineer the temperature. The sharper the shadow, the slower the expansion, the colder the matter. They had done it. They had created a stillness that the cosmos itself had never achieved. This brings us to the heart of the mystery, the superatom. What happens when you cool a gas of atoms to this regime? According to quantum mechanics, every particle is also a wave. Usually, these waves are tiny and messy, overlapping randomly. But as the temperature drops, the waves stretch out. They get longer. At 50 picokelvins, the matter waves of thousands of rubidium atoms stretch out so far that they completely overlap. They stop being thousands of individual waves and become one giant megawave. This is quantum coherence on a macroscopic scale. It is as if thousands of people in a stadium stopped chanting their own names and suddenly, as one entity, began to sing a single note. These atoms are no longer distinct entities. They are indistinguishable. You cannot point to one and say, this atom is here, and that one is there. They are everywhere in the cloud at once. It is a fragile, beautiful state of existence, a superatom that behaves according to the rules of the quantum world, yet is large enough to be seen by the naked eye. But this beauty is terrifyingly fragile. The slightest interaction with the outside world, a single photon of stray light, a whisper of heat, collapses the wave function instantly. The superatom shatters back into a boring classical gas. It is a window into the quantum realm that requires a perfect sterile vacuum to keep open. We have traveled from the frigid outposts of deep space to the controlled violence of the magnetic trap. We have touched temperatures of 50 picokelvins. We are so close to absolute zero that we can practically taste the void. We have slowed time itself for these atoms. And yet, looking at that final digit, the zero, we have to ask the question that haunts every physicist in this field. We are closer than anyone has ever been. But is the finish line real? Can we actually reach absolute zero, or is it a horizon forever retreating as we approach it? The laws of thermodynamics are whispering an answer that we may not want to hear. 2. The absolute zero barrier. We return to that stainless steel chamber not as a prison for matter, but as a gateway to a new reality. What you are looking at is not a gas. It is not a fluid, and it is certainly not a solid in any way you've ever experienced. It is a Bose Einstein condensate, a state of matter that exists only at the precipice of the impossible. In our previous chapters, we've seen how temperature is merely a measurement of motion. We've burned things to see them glow, and we've frozen them to shatter their bonds. But here, in this lab, we are asking a question that borders on the philosophical. Is there a bottom? Is there a point where the universe says, stop? A temperature so low that motion itself ceases to exist? We call this absolute zero. It is the theoretical limit of cold, the point at which atoms lose all their thermal energy and simply stop. At 0 Kelvin, or minus 273.15 degrees Celsius, the universe should freeze in place. But there is a catch. Because to reach absolute zero, to truly stop an atom in its tracks, is to violate the very laws that govern the quantum realm. This brings us to the barrier that stands between us and the absolute bottom, the Heisenberg uncertainty principle. In the subatomic world, nature enforces a strict trade-off. You can know where a particle is, or you can know how fast it is moving, but you can never perfectly know both at the same time. Think of it like trying to take a photograph of a racing car. If you use a fast shutter speed, you capture exactly where the car is, but the wheels look frozen. You've lost the sense of speed. If you use a slow shutter, you see the speed, but the car is just a blur. You've lost the position. To cool an atom to absolute zero, we have to slow it down completely. We have to confine it to a single point in space, stopping its momentum to zero. But if we know exactly where the atom is, stopped dead in its tracks, the uncertainty principle demands that its momentum become infinitely uncertain. If we force the position to be perfect, the momentum must become infinite. The atom would essentially tear itself apart with energy. Therefore, absolute zero isn't just hard to reach, it is theoretically impossible. It is a horizon we can approach, but never touch. We can get to within a billionth of a degree, but that last fraction is protected by the fundamental fabric of reality. So, we are left with a dilemma. We have created this exotic, fragile state of matter, the condensate. But we can't hold it for long. Here on Earth, gravity is our enemy. These clouds are so delicate that the slightest perturbation causes them to warm up and disintegrate. We usually have less than a second to study them before they fall apart and vanish. If we want to probe the deepest secrets of the quantum world, we need to go somewhere else. We need to go where gravity loses its grip, where the environment is ultra-stable, and where we can let these atoms float freely. We need to go to space. This is the Cold Atom Lab, CAL, a facility about the size of a cooler bolted to the exterior of the International Space Station. It is arguably the coldest place in the known universe. Inside this orbital freezer, scientists are performing experiments that cannot be done on Earth. Without the weight of gravity pulling the atoms down, the magnetic traps don't need to be as strong. We can use weaker fields to hold the atoms, which means we don't heat them up as much. In space are bows. Einstein condensate doesn't fall, it expands. It can last for 5, sometimes 10 seconds. That might not sound like much, but in the world of quantum physics, that is an eternity. It allows us to observe the quantum wave nature of matter with a clarity we have never had before. By pushing these temperatures lower and holding them longer in the microgravity of space, we are essentially turning the ISS into a giant quantum microscope. We are watching atoms behave like waves, interfering with one another like ripples on a pond. Which brings us to the ultimate question. Why go through all this trouble? Why spend millions of dollars to build a fridge in space just to watch a few atoms float around for a few extra seconds? What does the coldest matter in the universe actually do for us? The answer lies not in the cold itself, but in the precision that the cold demands. To create these states, we must master control over energy and matter at the most fundamental level. The technology we develop to reach these temperatures, the lasers, the magnetic traps, the vacuum systems, they are the building blocks of the future. They pave the way for quantum computers that can solve problems in seconds that would take today's supercomputers thousands of years. They lead to sensors so precise they can detect the gravitational pull of a mountain range from the other side of the planet, or navigate the deepest oceans without GPS. We aren't just chasing the cold. We are chasing certainty in an uncertain universe. And as the Cold Atom Lab continues its orbit, looking down at our warm, chaotic world, we are getting closer than ever to understanding the very nature of existence itself. Engineering the impossible. We left the last chapter staring into the heart of the absolute zero, a ghostly orb of matter stripped of its thermal chaos, behaving as a single, coherent entity. It is beautiful, certainly. But in the world of engineering, beauty is not enough. To survive, a discovery must do more than just exist, it must serve. For decades, the Bose-Einstein condensate, or BEC, was considered a delicate curiosity, a fragile flower that bloomed only in the rarefied air of the world's most sophisticated labs. But we are no longer just observing the quantum realm, we are learning to speak its language. And in doing so, we are transforming the abstract laws of physics into the tangible tools of the future. This is the transition from the era of discovery to the era of application. The quantum revolution isn't a distant prophecy, it is happening now, and it hinges on our ability to control these cold atoms with exquisite precision. We are moving from merely proving Einstein right to building machines that exploit the very strangeness he predicted. Consider the problem of complexity. Our best supercomputers are marvels of engineering, but they are fundamentally limited by the nature of reality itself. When they try to simulate the interactions of just a few hundred quantum particles, they hit a wall. The math becomes too heavy, the variables too numerous. It would take a classical computer longer than the age of the universe to model a simple molecule of caffeine. Enter the quantum simulator. By using a BEC, we can build an analog computer using the very building blocks of nature. We can arrange cold atoms into a lattice, mimicking the structure of a new material or a complex molecule, and simply watch what happens. We let the quantum mechanics solve the problem for us. This could unlock the secrets of high-temperature superconductors, revolutionizing how we transmit energy, or help us design drugs with a precision that is currently impossible. But the utility of cold atoms extends beyond the digital realm. It reaches out into the physical world, right down to how we find our way. Today, we rely on global positioning systems. GPS, a constellation of satellites beaming time signals from space. It is a miracle of modern life, but it is also a profound vulnerability. Those signals are weak, easily jammed or blocked by buildings and terrain. We are now engineering ultra-precise sensors using cold atoms that measure gravity itself. In an atom interferometer, we launch a cloud of these supercooled atoms into the air. We split their wave function in two using lasers, sending them on different paths and then recombine them. Because they are quantum waves, the interference pattern created when they recombine is exquisitely sensitive to the environment. These sensors can detect minute changes in gravitational pull. This means a submarine could navigate the oceans without ever surfacing for a GPS fix. It means a vehicle could drive through a tunnel knowing exactly where it is. It even allows us to look underground, mapping hidden caves, mineral deposits, or voids beneath the Earth's surface without digging a single hole. We are literally giving machines a new sense-gravity vision. And then there is the matter of secrets. In an age where data is the world's most valuable currency, our current methods of encryption are living on borrowed time. The computers of tomorrow, specifically quantum computers, will likely be able to shatter the codes that protect our banks, our hospitals, and our governments. But the same quantum mechanics that threatens our security also offers the solution. Using entangled particles, we can create encryption keys that are theoretically unbreakable. This is quantum key distribution. If a hacker tries to intercept the key, the very act of observing it disturbs the quantum state, instantly destroying the key and alerting the users that they are being listened to. We are engineering a lock that cannot be picked because the lock changes the moment you touch it. This is the engineering of the impossible, taking a phenomenon that was once a footnote in a physics textbook and turning it into a platform for the next century of innovation. But to appreciate how far we have come, we have to remember where we started. In 1924, Satyendra Nath Bose sent a paper to Einstein. It was a radical idea, Einstein expanded on it, predicting a new state of matter, but he doubted it would ever be seen. He thought the forces required to hold it together were too strong, that the temperatures were too low to ever be reached. For 70 years, it remained a ghost, a theoretical spectre haunting the margins of physics. Until 1995, when the teams at Giller and MIT finally coaxed the condensate into existence. They did more than just prove a theory. They proved that human ingenuity could decode the universe's deepest secrets to create its most extreme environments. We didn't just find the Bose-Einstein condensate, we built the cage to hold it, the lasers to cool it, and the eyes to see it. The universe is a place of incredible violence. It is born in fire, fueled by fusion, and torn apart by gravity. It is hot, chaotic, and relentless. But in our laboratories, standing amidst the noise of the modern world, we have created a sanctuary of cold order. We have found a way to pause the dance, to silence the noise, and to look at the building blocks of reality while they are at rest. We have mastered the cold. But as we look out from our laboratory islands, we are reminded that the universe is vast, and it is not cold. It is rushing toward an energetic future. We have learned to slow the atom down to near zero. But the ultimate test of engineering may not be in stopping things, but in keeping up with them. How fast can we go? Is there a way to break the ultimate barrier? Join us in the next chapter. We have reached the end of tonight's topics, and it is time to let your mind completely unwind. Whatever you learned tonight, let it fade into a soft hum as you drift off. Thank you for being a part of Night Shift Knowledge and sharing this quiet space with me. Remember to leave a topic suggestion for next time if you are still awake, but for now, just rest. Sleep well, and I will be here the next time you need to quiet your mind. Good night.